Check it.
Okay, welcome back. We're going to be talking about power functions and end behavior today. We're going to be working on section 6.3, and it's going to take 3 days to get through this. We're going to be learning how to graph functions of higher powers than what we're used to. And it's going to require us to start with small things and work our way up. So the smallest possible, simplest possible function is called a power function. And a power function is a function that is just simply y equals x to a power. So y equals x to the 0, y equals x to the 1, y equals x to the 2, so on and so forth. You can see I go all the way down to y equals x to the 10, and then I jump to y equals x to 1,000 and 1,001, and we'll talk about that in a minute. So what's the deal here? What is what is a power function and why is it useful? Well, we already know some power functions, like y equals x squared we know is a parabola. Okay, your very basic parabola there. Here's the thing. Every even power function is sort of a variation of this parabola. Okay, like for instance, here's y equals x to the 4th. It still kind of looks like a parabola. Look at it, right? It still sort of looks like a parabola, but it looks like a parabola with a flatter bottom. Here's the parabola again. It looks like you took the parabola, whacked it against the table, and made the bottom flat, right? And it also looks like you bent the legs in more. Okay, like they're not quite as wide as the original parabola. They're more steep. So two things happen when you go from a power of 2 to a power of 4. The bottom gets a little flatter and the legs get a little steeper. Now let's go to x to the 6th. Y equals x to the 6th. More flat down here, more steep on the sides, okay, compared to y equals x to the 4th. You can see it's, goes up faster, so it's a little more narrow because it's going up faster, and it's a little bit flatter at the bottom here. How about y equals x to the 8th? Even more flat on the bottom, even more steep on the sides. How about y equals x to the 10th? More flat on the bottom, more steep on the sides. Compare that to the original parabola, y equals x squared, and you can see a pretty big difference, right? It's really flat on the bottom, not just a little dented, and really kind of steep going up, almost not quite vertical, but going up pretty steeply. So how about we compare this now to y equals x to the 1,000th? 1,000 is an even number, so this would be an even power function. What do you think it would look like? Well, let's see. Things keep getting flatter and things keep getting steeper. Okay, hopefully you have a mental picture in your head. Now let's take a look. Yep, there it is. It looks like a rectangle. Okay, it looks like a complete, like these sides look completely vertical and this is totally flat. It looks like a rectangle. But if you get really close in here, okay, I'm gonna roll in here. If you get close enough, you zoom in enough, you'll see that it's actually not a rectangle. It actually is a curve if you get close enough to it. Okay, so it is curved, all right, and it's not vertical. It looks like it's vertical. Here we go back to the beginning here. It looks completely vertical, but it's not. It looks like it's just riding x equals 1 straight up. But if you get closer, x equals 1 right here, and you get a little closer and closer and closer, eventually, there it is. There's 1. It's actually a little bit, see, there's 1 right there. It's a little bit outside of it. It just looks like it's on top of it from a distance. So we say that this parabola here has something called an end behavior. End behavior is what the function does as it goes to the ends, okay? Off to the left, off to the right. So this function, as you move to the right, okay, as your x increases from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10 to a million to a billion to a trillion to infinity and beyond. As you go to infinity on the x, your y goes up, okay? So we say that as x approaches infinity, y goes up. Now y is this way. Your y goes 1, 2, 3, 4, 5, 6, all the way up to infinity as well. So this is the end behavior on the right side. For the right side, we say as x approaches infinity, comma, y approaches infinity. And now you know why I tell you don't use arrows in your work, because arrows mean something else in mathematics. What about on the left? We talked about what's happening on the right. What about on the left? On the left, going this way, as x approaches -1, -2, -3, -4, -infinity, as x approaches negative infinity, What are the y's doing? The y's are also going up. So y approaches positive infinity, or just infinity. And this thing right here is what's called the end behavior of the function. And this is what you have to write on the homework tonight. Okay? When they ask you for the end behavior, you have to write 2 sentences. Here's one sentence. Here's another sentence. Okay? What's going on the right? What's going on the left? So that's the end behavior and basic shape of all even power functions. They're all basically the same. They all have the same power, the same shape basically. They're all going up. See, 2, 4, 6, 8, 10, 1,000. They all have the same end behavior. As x goes to the right, y goes up. As x goes to the left, y goes up. And the way you write it is the way that I showed you. So now what about odd power functions? So odd power functions, the most basic one would be 3. What does that look like? Well, 3 is what's called a cubic function. X to the third is called a cubic function. It goes up on the right, down on the left. So you can think of a third power function as being almost like a parabola going up on one side and down on the other side. All right? It's like you took a parabola and you grabbed one side of it and bent it down, okay, causing it to look like this. So this side goes up, this side goes down. Now, if you look at all of the odd power functions that come after it, they all have this basic shape, and they all have the same end behavior. So let's talk about the end behavior here. As x goes to the right, okay, which means the values of x are going up, up, up to positive infinity. Now you don't have to put a plus for positive infinity, just write infinity. As x approaches infinity, y approaches what? It's going up. So the numbers are getting bigger and bigger and bigger, also infinity. But that's what's happening on the right side. On the left side, you can see something else is happening. As the x's go to -2, -4, -100, -1,000,000, as x approaches negative infinity, okay, what are the y's doing now? This time the y's are going down. So y is approaching negative infinity as well. And that's your end behavior. So what happens when you go to a higher power? Well, if you go to x to the 5th, which is the next odd power up, you look at it, it still kind of looks the same, right? Here you go. Now what's happening here? The legs are getting a little steeper, and the middle part, if you look at it, also getting flatter, right? So the same thing that was happening with the parabolas is happening with the cubics. And as you go higher and higher, this gets more pronounced. So x to the 7th, the legs are getting steeper, the middle is getting flatter. Y equals x to the 9th, the legs are getting steeper, they're looking more vertical, and the middle is even more flat. Okay, so take a wild guess. What do you think y equals x to the 1001, which is odd? What do you think that looks like? Well, let's take a look. Yep, it looks like that thing. It looks like a rectangle with one side bent down this way. Now, once again, if you zoom in enough, you'll see this is not really a rectangle. Okay, just like before. Now, one way to kind of remember this is that an even function is a Rocky and an odd function is a Travolta. This is a hard image to forget. So yeah, this is your cubic function, up on the right, follow the arms, up on the right, down on the left. That's an odd function, odd power function. And for the even power functions, you got both hands in the air, Rocky Balboa style, like that. Okay. So once again, end behavior is what you get when you decide to verbally say what's happening with the function. So here, the function's going up on the right. As x gets bigger, y gets bigger, and that's how you write it. And on the left here, as x gets smaller, or more negative rather, y gets more negative as well, and that's how you write that. Now, the next thing we want to talk about is, if you have a polynomial, what's the degree of the polynomial? It's not really written the proper way. You're supposed to write a polynomial from highest power to lowest power. So really, it should look like this. So this is actually what your polynomial should look like. The 4x, the negative 4x to the 7th that's in the middle here should have been first because it's the highest power, followed by the next lowest power, the next lowest power, the next lowest power, the next lowest power. So anyway, the point is you have a polynomial here and you want to talk about what degree it is. You have to look at what's called the lead term. And the lead term is the highest power term, which is going to be this right here. So this is a 7th power polynomial. That means it's odd. That means it's a what? Is it a Rocky or a Travolta? It's a Travolta. It's going up on the right and down on the left. However, you notice the coefficient is negative. It's a -4. Now what happens when you put a negative in front of a function? It flips it upside down. So let's go back to Desmos for a second. Okay, we have a x to the 7th power right here. There you go, there's your Travolta. But if you stick a negative right there, boom, what happens? Okay, he dances in the opposite direction. So now instead of going up to the right, up on the right and down on the left, it's up on the left and down on the right. Putting a negative in front of a power function flips it upside down. And the way to flip a power function upside down, okay, is to change which directions it goes up and which direction it goes up. It goes down. So where it goes up, it now goes down. Where it goes down, it now goes up. So if you have an even function, okay, but with a negative in front of it, instead of going up, it goes both sides down. With a cubic or odd function power, instead of going up on the right and down on the left, it's going to go up on the left and down on the right. Okay, so coming back to this problem up here, we know that this is a 7th power function because its lead term, its highest power term, is a 7th power. So we know it's a cubic shape. The shape is a Travolta, but it's not a regular Travolta, it's an upside down Travolta. So down on the right, there you go. And this is y equals x to the 7th, you know, a very rough sketch. Okay, you notice I didn't bother worrying about how steep it is or how flat it is in the middle. But the point is that you now know in a basic way what this function is doing. Okay, it's going up on the left, down on the right. So what's the end behavior? The end behavior is as x approaches to the left now, on the left side, negative infinity, y approaches, y is going up, infinity. And now you need to do it, you need to write this twice. On the right side, as x approaches positive infinity, meaning going to the right, y is going down. So y is approaching negative infinity. There's your end behavior. There's the degree of the function. These are all questions that are going to be on the homework tonight. If you're given something like this, what is the lead term? The lead term is -4x to the 7th. What is the degree of the function? The degree is 7. What is the end behavior? Well, draw yourself this little sketch and then realize, okay, here's the end behavior. Okay, let's try it with this one here. I'm not going to rewrite this one in order. Just look through this and find the highest power term. There it is, x to the 4th. So this is a version of y equals x to the 4th. So its end behavior should be the same as the end behavior of y equals x to the 4th, meaning up on both sides. So it's a 4th power function, and the end behavior is as x goes to the left, which is negative infinity, y goes up, which is y approaches infinity, and as x goes to the right, which is positive infinity, y also goes up, so y also approaches infinity, and there's your end behavior. Let's go down to this next thing here. So if you start with those power functions that I talked about, all right, how do you end up going from y equals x to the 4th to something crazy like this with all these terms here? Well, the fact is the highest term, the lead term, determines the end behavior. After that, all these other terms, all they do is they just kind of add more twists and turns. So check this out. Let's go back to Desmos, all right? And let's go to y equals x to the 4th. Okay, there it is. And we know the end behavior is up on the left, up on the right. Okay, as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches infinity. Okay. But let's say we start adding some terms to this. Like, okay, there's a 4th power term there. That's the original, you know, that's the main term there. But what if we add like minus 5x to the 3rd? What does that do to the shape? Well, you notice it adds in more stuff, right? Adds in more curves. Let me zoom out a little bit. So you see what happened is when I added another term, it created more curves, but the end behavior is still up and up. That didn't change. So I can add more terms here. How about plus 2x? Right? You can see it changes the middle a little bit, but it doesn't really change the overall shape of the function. If you zoom out enough, you see that the function still has that kind of parabola look to it. No matter what, your end behavior is still going up to infinity on this side, up to infinity on this side. And you can add some more numbers to it. Here, like plus 3 or something. It doesn't change. So you have this crazy long function now, but it's still a 4th power function. Okay, at its core, okay, at the heart of it, it's still just y equals x to the fourth. If you just delete all this stuff, it's still going up on this side and up on this side. Now let's try it with an odd power function, like x to the seventh. Okay, there you go. There's your Travolta, right? But if you add more stuff to it, like plus x to the sixth, for instance, okay, well, maybe put a number there, 4x to the sixth, or 2x to the sixth, all right? You can see it adds a little curve in there, but it's still going down on the right, sorry, down on the left and up on the right. It's still a Travolta if you look at it from far away. It's still kind of going down and up, right? That part is not going to change no matter what. So I could add more terms, minus 5x to the fifth, plus 3 or 4x to the fourth. I'm just doing random stuff here. Minus 3x to the third, minus x squared, plus 2x plus 1. Who cares, right? Anyway, what that creates is more curves and more stuff going on in the middle. But when you zoom out enough, and now if you look at it from this scale, yeah, I've introduced some curves and some things in the middle, but it's still a Travolta. It's still going up on the right, down on the left. That part has not changed. So at its core, at its heart, it's still just y equals x to the seventh with a whole bunch of added stuff to it. So you look at that. That's just y equals x to the seventh. I'm going to paste back what I just took off there. See, it changes it a little bit, right? It changes what's going on in the middle, but it doesn't really change that much. Okay, this part's going way up to 1,000 here. That's why it's going off the screen before. And this squiggly stuff is in here, but it's not showing because I've zoomed out so much. But anyway, you get the idea, hopefully, that it's still y equals x to the seventh, just with extra bumps in the middle. So this is kind of the moral of the story here. Everything that every polynomial that we have has a highest degree term called lead term. That lead coefficient and lead term determine the end behavior, which way the function's going, up, down, left, right, that sort of thing. And adding more powers just creates more twists and turns, right? And those extra twists and turns, by the way, can create more x-intercepts, which we'll talk about tomorrow. All right, so let's do a couple of just homework questions here just to make sure we got this. State the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Okay, so for number 2 here, is this a polynomial of one variable? Well, there's only x's in here, no other letters. So yes, it is a one variable polynomial. If so, what is the degree? Well, the degree would be the lead term. What is the power of the lead term? It's a 7th degree. So state the degree, 7th degree. The lead coefficient is -10, or the lead term is -10x to the 7th. I don't know if they want the term or the coefficient. Either way. All right, and that's it. All right, how about this one here? This has got x's and y's in it, and if it has more than one letter in it, it's not a polynomial in one variable. The stuff we're going to be talking about has to be one variable. So as soon as they add another letter in there, we can just basically say this is not one variable, has a term for xy. Okay, and that's what you're going to write for that homework assignment. All right, how about for these? Let's do a couple of these. Describe the end behavior of the graph of each function. 57. What's the power of this function? Well, the highest power is 4th power. So for 57, you're going to say this is a 4th power function. And now you have to describe the end behavior. Well, the end behavior of a 4th power function usually is up, up, right? However, there's a negative on a -5, which is the coefficient here. So this is actually an upside down or negative 4th power function. So it actually looks like this, like that, right? Well, should be going through the origin. So what's the end behavior? The end behavior is as x goes to the left, something's going to happen. And as x goes to the right, something's going to happen. Now, in both cases, what's going on? In both cases, we're going down. So y going down means y is going to -infinity for both of these. And that's your end behavior. That's your degree. And this is your sketch that you should be able to do. We'll try 58 here, or the lead term rather is 2x to the 5th. So it's a 5th power function. There's no negative on the lead term, so it's going to be your typical Travolta, right? A little flat in the middle, but that's fine. What's the end behavior? Well, it's going up on the right, down on the left. So as x approaches the left, which is negative infinity, y approaches up, which is positive infinity. As x approaches the right, which is positive infinity, y is going up, which is also, oh, I'm sorry, I messed up here. As x goes to the left, y is going down. Sorry. As x is going to the left, y is going down, so this is negative infinity. As x is going to the right, y is going up, and that's positive infinity. And there's your end behavior for 58. Okay. Let's try 62. This is they're trying to mess with us here. The first term is not the lead term. The second term is the lead term. See, the seventh power is actually here. And it's a negative seventh power. Look at that. Okay, they're trying to fool us. So if you're paying attention, that's the highest power. So this is a seventh power. This is the lead coefficient, right? Sorry, the lead term right here. Its coefficient, which is -5, is negative. So it's going to be upside down. So it's a negative seventh power. So it's an upside down Travolta. Instead of going up to the right and down to the left, it's actually going to go up to the left and down to the right. That's your power. That's your, what do you call it, your end behavior. See, the end behavior, all you have to worry about is whether it's odd or even, whether the lead term is odd or even. And whether it's a negative or positive, tells you if it's upside down. Now, once we know this, we can do our what do you call it, end behavior. As x approaches, I like to do the left first. So as x goes to negative infinity, which means going to the left, comma, y is going which way? Well, y is going up, so positive infinity. As x is going to the right, which is positive infinity for the x, what's the y doing? The y is going down, which is negative infinity for the y. And there you go. There's your end behavior. Okay, we're done. See you later.
Check this.